Hello and welcome. Today we're going to talk about the chain rule. The chain rule is a very important piece of differential calculus, and the purpose of the chain rule is to tell you how to take derivatives of composite functions. So what is a composite function? Well, let's imagine that you have two functions, f and g. You can take these two functions and you can do various things to combine them, like add them, subtract them, multiply them. Another thing you can do is you can take the output of one function and make it the input to the other function. In particular, you can do this by saying f of g of x, so that g, or the output of g, the result of computing g, is then the input to this next function f. And this is function composition, and you can use this to define a new function, and let's call it h of x. So this new function, h of x, has been defined as the composition of f with g. And another way of writing this is f and then circle g. That circle means function composition. Okay, so I told you that the chain rule is important, or is used to compute the derivative of functions like h, when this function can be written as the composition of other functions. And let's see what that looks like. The chain rule tells us that the derivative of this composite function can be expressed as the derivative of this first piece evaluated at the inner function, or at the inner piece, multiplied by the derivative of the inner piece. Okay, so this here is a statement of the chain rule, and there's some notation here that's probably unclear at this point, but that's okay. We're going to explain and unpack by going through a couple of examples. So here we go. Example number 1. We'll start off with something simple. Let's start by defining two functions, f. We'll call this guy 3x squared, and g, let's make this 4 plus 2x. Okay, so I'm going to define my two functions, and then I'll use those to compose, or I'll compose those and make a new function, x. And in fact, I'm going to define h. I just said x. I'm going to define h as the composition of f and g. So I'm going to put g inside f. Let's see what that looks like. Well, f, the function, is a rule, or here where I'm expressing the rule. It says give me any input. I'm going to take that input, I'm going to square it, and multiply that by 3. So if you hand me, instead of an x, if you hand me a g of x, I'm going to square that g of x and multiply it by 3. So h of x then is equal to 3 times g of x squared. All right. Now let's use the definition of g to plug in here and re-express this thing entirely in terms of x. So if 3 times, now g, the definition of g is just 4 plus 2x. And there we go. So we have this completely expressed in terms of x. I can, if I like, expand this thing out. And what do we get? 3 times 16 plus 8x plus 4x squared. Hope I'm doing that right. I didn't do that right. So 4 times 4 times 2 is 8. Let's make that 16. Sorry for that. Okay. And then finally, that is 48 plus 48x plus 12x squared. Great. So I composed f and g. I came up with a composite function, h of x. And as a side note, if I had put f inside of g instead of g inside of f, you generally get something different. But we're not going to do that here. Okay, so here's my composite function. And I told you that we use the chain rule to compute the derivative of functions like this. Well, I already know how to compute the derivative of this function h. And let's just do that because we know how to do it. I can do this very straightforwardly. This is just a sum of 3 terms, each of which is just a simple coefficient and a power. So 48, which is a constant, derives to 0. 48x derives to 48. and then 12x squared derives to 24x. Okay, so I already know how to do that. This will serve as a check for us when we apply the chain rule. Okay, great. Let's write down the chain rule again, just for practice. It says that dh dx is equal to df dx evaluated at g of x times dg dx. Okay, so let's look at all these pieces here. This is the thing that I want, the derivative. I know what g of x is, that's given here in the definition. I don't yet know what df dx is, and I don't yet know what dg dx is. So let's compute those two things. F is given as 3x squared, so df dx then is just 6x. It's just a power rule. Okay, and likewise the derivative of g with respect to x is equal to 4 goes to 0, and then we just get a 2. Okay, so now this is the part that takes a little bit of thinking, so let's be careful. This piece here means I want to apply this function, df dx, to the argument g of x, all right? This right here, df dx is equal to 6x. This is a function. I could also write it this way, f prime of x. It's some function of argument x, and it says give me an argument like x, and I spit back at you 6 times that argument x. So if the argument is instead g of x, what do you get? You get 6 times that argument g of x. Okay? Then we multiply by dg dx, and dg dx in this case is just 2. So we're almost there. dh dx is equal to 6 times g times 2. Let's substitute in for g in terms of the definition 4 plus 2x, and we get 6 times 4 plus 2x times 2, and we'll expand that. And what do we get? 6 times 4 is 24, times 2 is 48, plus 6 times 2 is 24x. And lo and behold, I get the same thing using the chain rule as I did if I did this kind of just grind through the problem. Okay, so great, that works. So that's a positive. However, you should ask yourself, why should I bother learning this chain rule business when I already knew how to compute the derivative? Okay, so what's the use of all this business? Let's go through another example, and we'll see specifically why, or one good reason why we need to know the chain rule. And oops, I am out of paper. Let's use this. 3x to the 100. All right, here we go. Okay, example 2. So again, we're going to define our f and our g. And this time I'm going to make it, instead of 3x squared, I'm going to make it 3x to the 100. And g, instead of, well, we'll just keep g as the same, 4 plus 2x. Okay. The business of constructing the function h is really the same, f of g of x. So g is going to be the argument of the function f. So instead of taking x to the 100 and multiplying by 3, I take g to the 100 and multiply by 3. Okay, and now let's substitute in for g. G is equal to 4 plus 2x. So we'll say 3 times 4 plus 2x, all now to the 100. Okay, now in the previous example, what did we do? At this point, we had plugged in for g, and then we expanded this out into a polynomial. We could do that here. We could expand this 4 plus 2x to the 100 into a polynomial, but it's going to be, what is that, 101 terms. So I could do this, but I'm not going to. All right, so this is something I know how to do, but I just don't want to do this. So instead, I'm going to turn to this new tool, which is the chain rule, to compute this thing in a different way, which is hopefully going to be a lot less work. Let's do that. So dh dx is equal to df dx evaluated at g of x times dg dx. Okay, this is reminding us of the chain rule definition. And we know all these things except for this derivative here and this derivative here. So let's go ahead and compute those just like we did before. The derivative of f with respect to x is equal to 300x to the 99. I drop that power by 1. And dg dx is equal to, again, just the number 2. Great. Now I can plug these things in and get dh dx is equal to df dx. This function which is the derivative of f, is going to be applied to the argument g. So instead of 300x to the 99, it's 300g to the 99. So 300 g of x to the 99 times dg dx, which is, again, just 2. All right, now we can plug in for g. The definition of g here is 4 plus 2x. So dh dx is equal to 300. We plug that in, we get 4 plus 2x to the 99 times 2. And I suppose it makes sense to just write this as 600 times 4 plus 2x to the 99. Okay, so I didn't even have to touch this 101 terms or this 100 terms in the derivative form, and I arrive at the derivative of the composite function. So the chain rule has shown its use in this case because I can attack things that I could attack previously, but would take me pages and pages and pages of work, or would certainly take a lot more thinking. You'd have to use the binomial expansion and etc. I mean, you could certainly do it, but this is obviously a lot cleaner. Okay, let's do a third example. We need a piece of paper. Here we go. Okay, example 3. Let me try that again. Example 3. Example 3 is going to be a little bit different in flavor. What we're going to do here is, instead of me giving you the two functions that you will compose and produce function h, I'm going to start off with the function h, and we're going to try to figure out how to re-represent that function as a composition of two piece functions, and then use the chain rule. So we're going to start out with this function h of x, defined as 1 plus x cubed square root. Okay, so how do you do that? The answer more or less is and this is maybe unsatisfying, but you sort of look for the obvious groups. Okay, another way of rewriting, or another way of writing this function is as 1 plus x cubed parentheses to the 1/2. And here the parentheses maybe make it a little bit more explicit that this right here is an important group within the function h. Okay, and it suggests itself as a natural chunk to pull out when I'm forming this decomposition. So let's take this chunk and let's treat that as the first function, or rather the inner function in our function composition. So let's call that thing g. All right, so g of x is equal to 1 plus x cubed. So when you're computing h, what you do is you take x, you cube it, you add 1, and then you take all of that and you take the square root of it. So in my composite form, I'm first going to compute g, which is take x, cube it, add 1. Now I have that result. Then I'm going to take that thing and pass it into f. And all f has to do, f just has to do this last little bit of work, which is to take the square root. And I'm going to write x to the 1/2. You could write square root of x, either way. Okay, so hopefully you can see that I've successfully decomposed h into an inner and an outer function. All right. In this case, we actually don't have any tools for computing this in some kind of brute force way, so we're going to have to appeal to the chain rule. So the derivative is equal to df dx evaluated at g times dg dx. Okay, here we go. So as before, we know what g is, we don't know what df dx is, we don't know what dg dx is. So let's compute those here. I guess I'll fly these guys up here. So df dx is equal to, and then this is again just a power rule, so I get a half x to the minus 1/2, and dg dx is equal to 3x squared. Okay, cool. Now we can substitute these things in to our chain rule. So dh dx is equal to df dx. That's my function, which is the derivative of f. It takes an argument, it raises it to the minus 1/2 power, and then multiplies that by 1/2. When the argument is g, that means I take a g and I raise it to the minus 1/2 power, and then I multiply that by 1/2. Then I multiply by dg dx, which apparently is 3x squared. Great. Let's substitute in for g. The definition of g here that we extracted is 1 plus x cubed, so I've got a 1/2 1 plus x cubed to the minus 1/2 times 3x squared. Okay, so this is all in terms of x's. We can simplify this a little bit maybe, if you like. And let's put this square root thing on the bottom, and we'll keep the x squared on top. And we could rewrite it as 3x squared over 2, and then we've got a 1 plus x cubed. And let's write it this way instead, just for fun. So here we've computed the derivative of this function by first breaking it into a function composition, or re-representing this function as a function composition, and then using the chain rule here to compute the derivative. Okay, thanks.